Hello, we're going to talk today about Chapter 11 and a little bit about Chapter 12. And Chapter 11 talks about transistors. And the transistor was invented in the late 1940s, and its invention was credited to three Bell Laboratory scientists, John Bardeen, Walter Brattain, and William Shockley. Transistor is a contraction of the word transfer and the word resistor. Basically, two types of transistors, the bipolar junction and the metal oxide field effect transistor. Both are useful, but we'll just talk about the first one, the bipolar junction transistor, in this chapter. There's two types of bipolar junction transistor. They are the N and the P, the NPN and the PNP. And of those, we'll just discuss the NPN. So with the symbols here, we have three leads. There's the collector, the base, and the emitter. And the NPN is shown on the left, and the PNP is shown on the right. With the NPN, the arrow is pointing outward. With the PNP, the arrow is pointing inward. You can remember NPN is not pointing in. NPN is not pointing in. Transistors are like diodes. They're not linear. They have four modes of operation. One is called saturation, one is called cutoff, one is called the active range, and one is called the reverse active range. They basically, bipolar junction transistors control the flow of current. MOSFETs control the flow of voltage. While the discussion of BJTs is fundamental to further study, most transistors today use MOSFETs, since they typically do not use higher currents and therefore the heat that are generated with BJTs. So a bipolar junction transistor has three doped regions. They're sandwiched between, the base is sandwiched between the collector and the emitter. This is what it looks like. There's an emitter, there's a collector, and there's a small sandwiched region in between the two called the base. And it works something like this. You have a bunch of power coming in, and you have a control, and you have power going out based on the control. You can turn the control up and down, and it lets the power go in or not go in. Something like this, a faucet, you could not possibly control the flow of water out of a faucet very easily, except with the handle. And you can turn the handle, but you would have a hard time controlling the flow if you didn't. So you'd have a lot of flow or a little flow based on the position of the handle. And this is the amplifier of the base. So for a little current in the base, we control a large flow of the collector to emitter. So you have positive current coming down here and a small I coming in here, and you have a small IE coming out here. If you have a larger current coming in the base, you have a larger current coming down the collector and a larger current going out the emitter. So that's how it basically works. So the circuit basically works with a amount of current and amount of voltage from the B to E points. The B to E junction is forward biased in the figure below, and the BC is reverse biased, and the result is a forward biased transistor. In other words, you get flow if you put more voltage here than you do here. And it's, again, the magic number is 0.7 volts. So that's the electron hill that we talked about before. And we can go through the physics of it, but basically it's, if you put a higher voltage to the B than to the E, you're going to get flow. If you have a positive up here and you have a B to E positive, you're going to get flow with an NPN. Okay, so this would be a circuit that you could look at, and you have three currents. You have the current of the collector, the current of the base, and the current of the emitter. The gain of this circuit is called, the gain in the current from IB to IC is called beta. And there's a DC beta and there's an AC beta, but basically we just call it beta. And it's the ratio of the current coming down here to the smaller current there. And so these values of beta can be anywhere from, it's a number bigger than 1. It's 50, 100, 125, in that range. But it's something that basically you get a multiplication effect of current. Okay, so here we have a beta of IC over IB of 3.65 milliamps over 50 microamps, and we have a beta of 73. So that's our multiplication effect. So here, as long as our VBB is greater than 0.7 volts, there's a flow, and we have the 0.7 volts B to E, so that uses up 0.7 volts, and we can calculate what our IB would be in this circuit, and then we could calculate, if we knew the beta, what our IC would be. So we can write voltage across from RB to 0 volts is 0.7 volts, and IB is VBB minus VBE over RB. We can also write VCE as VCC minus RC, and that's the voltage. VCE is the voltage across the transistor. We can also write VCE is equal to VCC minus IC RC, and those are the equations that you can use to find out where we're at with our voltage across VCE. Okay, so here we are given beta. It says determine IB, IC, IE, VBE, VCE, and VCB if beta is 150. So we're given beta, and we know that the voltage from here to here is 0.7 volts if this is positively biased, and it is because this is greater than 0.7 volts. So you got to check to see if this voltage is greater than 0.7. If it is, then we have 0.7 volts across here, and that would then give us a IB. We could calculate it. It's VBB 5 minus VBE 0.7, and that gives us the current through here. That's IB. And then you can calculate IC, which is 150 times that, and that gives you the voltage across IC. Now IE is IC plus IB, and that gives you the current there. Now I can find the voltage across from C to E, which is the value of how much we amplified the circuit, and it's VCC minus IC times RC. So here our VCC is 3.55 volts. And we also can calculate VCB as 2.85 volts, which is this minus 0.7. Okay, now try the same thing with changing the beta, and you'll see some differences. All right, so if you look at a transistor circuit like this, you might think of it as a ball field, where you're going to have a high wall on the left foul line and on the right foul line, and you can't hit the ball outside of the field of play. So you're either going to hit it up here, you're going to hit it out here, or you're going to hit it down here. Now, if you hit it down here, this is along this wall. You can't hit it outside the field of play, but you can hit it along this wall. This would be a switch that was open. If you hit it out in the middle, that would be a switch that was as an amplifier. That would be a bipolar junction as an amplifier. And up here would be as like a switch that was closed. Okay. So this is called saturation. That means the switch is closed. Current's flowing. Here you're in cutoff. There's no current flowing. Or out here you're doing an amplification. In between the two, there's a load line. So you're going to hit the ball somewhere along this load line. Okay. So here, we're going to ask the question, determine if the circuit is in saturation or not. All right, so what do? Well, you find IC and see if it's IC set, and when it's saturated, in other words, when you're along this wall right here, IC is a big number and VCE is a very small number. So if you do that, you say, okay, what is IC set? Is VCC minus VCE sat, or 0.2 volts, divided by RC, or 9.8 milliamps. Now we go through and we calculate and see what we have here. And if we do our calculations and this number is greater than this number, we hit this wall. In other words, we can't go above this number right here. We can't go bigger than IC sat. So that's our number. And if we go above it, that means we're saturated. So if this number is bigger than this number, you're in saturation. You hit it along the wall and you can't go any further. Next is a switch. The wall was hit. Okay, so again, we're going to go down through and we're going to look at some other examples as well. In cutoff, the voltage across in cutoff, there is no current, and the voltage acts like we're down in this range right here. So in saturation, it acts like a closed switch. In cutoff, it acts like an open switch, and all of our voltage is across there's no current flow, and all of our voltage is across from here to here. Okay. So here's some problems that you can work, and we'll look and see what we can work on these and see what we can find with the IC set, the VCE. And you can work these yourself and see what you come up with, and we'll come back and look at them. Okay. Find out whether these circuits are in saturation or not. Okay. So the other part of this is talking about semiconductors is operational amplifiers. And with operational amplifiers, we're going to look at these triangles, and we're going to say, okay, if I put in a signal and I get an output from these, I can actually have a very high amplification if I want to, a very low amplification if I want to, based on the value of these resistors. Now, an operational amplifier is nothing more than transistor to transistor, where you amplify and then you amplify again, so you get a very high amplification, but then you trim that back based on the various values of these. So your V out over V in is, for a non-inverting amplifier, is this ratio right here of these resistors, and for an inverting amplifier, it is this one right here. For the non-inverting amplifier, it's this equation right here, and for the inverting amplifier, it's this equation right here. So that's wrong. Equation for the inverting amplifier is right there. Okay. Now, why would we even talk about this? It's because we have devices that we have in the field that basically do conversion from frequency to current, or from voltage to voltage, and basically all those devices that you would find, a little card that would do that, use this concept of an op-amp, an operational amplifier, to do those types of conversions. So basically these are the Legos or building blocks of amplification and conversion from one type of a signal to another. Current to voltage, frequency to voltage, voltage to frequency. All those use operational amplifiers, and that's why I wanted to talk to you about operational amplifiers. That was it. Take care and have a good day.